Hi everyone. In this first video, we're going to talk about covariance. Covariance is a quantity that gives us some information about the relationship that two different variables have with each other. In this video, we're going to talk about exactly what covariance is, how to calculate it. We're going to talk about what it tells us about the relationship between two variables, and also importantly, we're going to talk about what it does not tell us about this relationship. And finally, armed with this new information, we're going to tackle a couple of examples that involve the calculation of covariance. Before we actually get into the definition of covariance, let's motivate it a little bit and talk about exactly what we're trying to measure. So say we have a data set with data points xi, yi, right? We have n points, say. And what we care about is how x and y kind of vary with each other. So let's say we have a case that looks like this, where you have x and we have y. And we have data looking like this. So basically, for low values of x, we have low values of y. And as x increases, we see that y increases as well. In this case, it's very clear that there is a positive relationship between x and y. But this doesn't necessarily have to be the case. We can look at a different example potentially where we have the data looking like this. So for low values of x, we actually have high values of y. And as the value of x increases, we see that the value of y actually comes down. So in this case, we have a downward relationship like this. And it's also possible for neither of these to be the case, right? We could say for no matter what the value of x is, we see that the value of y stays fairly constant between, I guess, a particular range. And in this case, we see a fairly flat relationship between x and y. So in each of these cases over here, we say that there's a positive relationship. In this case, we say that there's a negative relationship. And in the final case, we could just say there's no relationship between x and y. So this is exactly kind of what we want to get from the concept of covariance. We want a quantity that will basically tell us, are these two variables related? Do they vary positively? Do they vary negatively? Or are they kind of not related to each other? So with that in mind, let's step into the actual definition of covariance. It's basically the measure of the relationship between two variables. So you have a covariance that's typically defined between two specific variables. In other words, you can think of it as a measure of the joint variability of two variables. And if the covariance value is positive, that means that the variables tend to move together in the same direction. If the covariance is negative, that means that they tend to move in opposite directions. Now, covariance is actually very good at conveying the direction of this joint variability, but it is not very good at conveying the strength of the relationship. That is to say, you could have covariance, you could have like a positive or a negative value, or you could have a zero value. And that basically gives you all the information that we saw on the previous slide. But it isn't very good at conveying the strength of the relationship because the quantities x and y involved are not normalized. And in order for this quantity to actually give you a good sense of how strong the relationship is, this quantity would have to be normalized. But yeah, with this in mind, with this information about covariance, let's go forward. This is an example of what covariance could look like. So we have over here on the x-axis the attendance of students in a particular class. And on the y-axis, we have the score that they obtain in a particular examination. And in general, over here, we see that for low values of attendance, we see lower final scores. And for high values of attendance, we see higher final scores. So basically that shows us that we have a relationship very similar to what we saw in the case, in the positive case that we saw a couple slides ago. We see that there's a general upward trend. The more you attend class, the higher your score is. And so this is something that can be established by our covariance metric. The covariance over here would have a positive value. You can take my word for it now, and then we can look at some examples later on to see how this actually works. Now, to be clear, this is just one variable among many that could affect the score, right? There are other variables that empirically, for people who study things like this, they see that other variables such as parental income, education, etc., could potentially affect your performance in class, not just merely your attendance in class. So one thing we could do is we could actually look at all of these independently. We could, in the place of attendance on this x-axis, we could replace it with parental income. We could replace it with parents' educational background or maybe years of education if we were looking for a numeric value. And then we could kind of find the covariance between each of those variables and the score. And then we could see whether they have positive or negative values or whether they have no impact at all. So over here, this actually gets into the calculation of covariance itself. So far, we've been talking about positive, negative values of covariance, but now we want to get into the real deal of how do we actually calculate this. So we have a formula for variance. We have, it's pretty well known. Sigma squared is equal to the sum of x minus mu, where mu is the mean, the whole squared, divided by n, where n is the number of samples. So this is our kind of population variance. For covariance, on the other hand, we computed slightly differently. So we can see the similarities to the above formula. We see that we have xi minus mu x and yi minus mu y. The reason we have both of those is we have the mean for one variable, the variable x, and we have the mean, this is variable x, and the mean for the other variable, variable y. And then we divide this entire quantity by n minus 1. Now you might ask, and it's a good question, why are we dividing it by n minus 1? And the reason we do that is because it's been shown empirically, or otherwise as well. There are mathematical proofs for this, which are beyond the scope of this particular video. But I would encourage you to search for it on Google as well. It turns out that using n minus 1 over here actually gives us an unbiased estimate of the variance, in this case, the covariance. We can talk a little bit about why exactly that happens. So suppose we're sampling data points. Suppose we have an entire population, which is basically data points, say on a line. Let's keep it simple. Let's talk about one dimension for now. Now, if we were trying to calculate the mean from this sample, and we wanted to do this a number of times, we would sample a set of points and say we would sample, let me change the color here, the yellow. So we would sample this, this, and this. The first time, we would get a particular value of the mean. The second time, maybe we'd sample this, this, and this, and we would get another value of the mean. So overall, the mean that you get if you do this enough times will be a good estimate of your population mean. Now, that is not necessarily the case for the variance, because suppose we had our first sample where we sample point A, B, and C. We see that the mean for the sample lies, I guess, somewhere in this area. And the mean for the overall population is somewhere around here, say, right? Now, when we talk about the variance, if we're trying to estimate the variance from the sample, we see that there is actually a much smaller variance if we were to consider this as the mean. The actual variance, when you look at the population, the actual variance of the given points is significantly higher because the mean is far to the right of these 3 points. So what tends to happen is that the variance is always underestimated if we do this kind of like sample-based approach. And it's been shown that if you take n-1 instead of n, you end up with a much more unbiased estimate of the variance, or in this case, the covariance. So that was a little bit of a digression. So in this case, we have x and y being the independent variables. We have n being the number of data points in the sample. We have mu x being the mean of the quantity x, and mu y being the mean of y, which in this case is the dependent variable. So as we said earlier, since we aren't normalizing the covariance value, it doesn't really convey useful information about the strength of the relationship. I should say that over here. That seems to have been messed up. The strength of the relationship between two variables. And when we're talking about two jointly distributed random variables, x and y, we can define the covariance in terms of the expected value of x and the expected value of the overall difference between x and the means, as shown over here. So let's take a little bit of an example. Let's do this on a different slide before we come here. So we want to say calculate the covariance for the following data set. We have x is 2.1. Let me write this down on a new slide. So let's go back. 2.1, 2.5, 3.6, and 4. And y, in this case, is 8, 10, 12, 14. And then the mean over here is, we can calculate from these values, it turns out 3.1. And the mean over here is 11. So how we're basically going to go about calculating the covariance in this case is we're basically going to subtract each of these quantities from the mean, multiply them together, right? So remember what we said. We said sigma xi minus mu x, yi minus mu y for all I divided by n minus 1. So what that's going to give us in this case is we're going to have 2.1 minus 3.1 multiplied by 8 minus 11 plus, that's 11, sorry, 2.5 minus 3.1 into 10 minus 11 plus, just making sure, yep, because doing live math is always 3.6 minus 3.1 into 12 minus 11 plus 4 minus 3.1 into 14 minus 11. We can calculate these. So this is, sorry, I think I need to make this a little bit clearer. I could remove that. Let's just say this is 8 minus 11, not plus. So that would be minus 1 into minus 3 plus minus 0.6 into minus 1 plus 0.5 into 1 plus 0.9 into 3. Of course, this whole quantity divided by n minus 1, which in this case is 3. So all of this divided by 3 again, which is equal to 3 plus 0.6 plus 0.5 plus 2.7 divided by 3, which is equal to 5.7 plus 0.6 is 6.3, plus 0.5 is 6.8 divided by 3, which is equal to 2.2, I want to say 2.267. So, okay, yeah, turns out we were right. Okay, so this is one example of how to calculate variance. Let's take maybe similar values, but let's try and calculate in a different case, right? So we have, let's take the same values over here, 2.1, 2.5, 3.6, and, 4.0. And the mean is 3.1. And for y, now let's take 5, 3, 2, and 1. So what is the mean in this case? The mean would be 5 plus 3, 8, plus 2, 10, plus 1, 11 divided by 4, which would be 2.75. I'll change my color. All right, so how do we calculate the covariance in this case? So, so we have, again, let's write our formulas, xi minus mu x multiplied by yi minus mu y, the whole thing divided by n minus 1. So what does that look like right now? So that looks like 2.1 minus 3.1 into 5 minus, this is a slightly hard number to deal with. So yeah, okay, let's just keep it as it is. 5 minus 2.75 plus 2.5 minus 3.1 into 3 minus 2.75 plus 3.6 minus 3.1 into 2 minus 2.75 plus 4 minus 3.1 into 1 minus 2.75. And this entire thing divided by 3. I am just going to use a calculator for this. So let me just pause this recording. Feel free to pause it as well, but I am going to calculate this and then I'll put the answer. Okay, so the answer that we got was negative 0.7625. And what that means in this case is that the quantities x and y are negatively, they vary negatively with each other, which means as x increases, y decreases, which is kind of what we see over here. So that's another example of how to calculate covariance, and that hopefully these two examples, they're fairly easy, but between the two of them give you a sense of what covariance is and how we can calculate it for data sets that are of the nature that we've seen over here. So finally, we just want to talk a little bit about the applications of covariance. Covariance is a useful quantity when we're talking about feature selection and algorithms. When we talk about machine learning, there's the idea of principal component analysis, which basically helps us reduce the number of features that we have in our model that'll help prevent overfitting and basically make sure that our model doesn't have too much variance in it. Covariance is a concept that's used in finance. When we're talking about different asset classes, when we're talking about different types of assets, different, for example, even different stocks, when we want to see how two assets vary together, you're interested in making sure that your portfolio is balanced and diverse enough that you don't have too much risk concentrated in assets that will move up or down together. So that's another area where we use covariance. And finally, it's also used in molecular biology, it's used in genetics in order to study secondary, tertiary proteins or RNA structures. This is not something that we have too many examples about, unfortunately, in this lecture, but it does seem very fascinating. All right, see you in the next video, and thank you.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150+ instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full-stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today